Welcome back to the Deep Dive, your shortcut to being truly well-informed on the bleeding edge of AI. Today, we're taking a deep dive into an area that often feels, well, almost like magic. The incredible advancements in large language models. Just think about it for a moment. It wasn't that long ago that these models were mostly just generating coherent text for basic chat. Now we're seeing them solve competition-level math problems that stump most humans, ace complex programming challenges, and undertake really intricate multi-step reasoning. It's an astonishing leap in capability, really a testament to relentless innovation.
Indeed, and what's truly fascinating, I think, is that behind these seemingly magical superpowers, there's this continuous, rigorous push in training methodologies. A significant part of that push involves a paradigm that has become absolutely central to their development: reinforcement learning, or RL.
RL, right?
It's the engine that allows these models to develop the capacity for deeper, longer, and more accurate reasoning processes. Think of it as a sophisticated feedback loop, where the model learns to generate responses that are rewarded for their quality or accuracy, much like how we learn through feedback.
Okay, let's unpack this then. Today, we're taking a deep dive into a brand new reinforcement learning algorithm, one that's poised to fundamentally transform how we train these massive language models, especially those intricate mixture of experts or MOE architectures that are becoming so prevalent. It's called Group Sequence Policy Optimization, or GSPO.
GSPO.
Our primary source for today's deep dive is a groundbreaking paper from the Qwen team at Alibaba Inc., published just a few days ago, July 29, 2025. This research, as you'll soon hear, looks like a really significant step forward.
Yeah, our mission today is to thoroughly understand the technical breakthroughs of GSPO, specifically how it fundamentally improves upon existing, widely used methods like GRPO, and its significant implications for the future of large-scale LLM training. We'll be strictly focusing on the technical mechanics and performance aspects.
Exactly. Technical mechanics and performance.
And for those of you who want to stay updated on the absolute cutting edge of AI and ML research papers, remember you can always visit our webpage, neuralintel.ai. That's linked in the bio. We curate all the latest findings there, distilling them for you.
Right. So if you've ever found yourself wondering how these cutting-edge LLMs get so incredibly good, or what the actual, nuts and bolts of their training look like under the hood, well, this deep dive is going to shed some serious light. We're going to cut through the complexity and give you the most important nuggets of knowledge, stuff that will genuinely shift your understanding of state-of-the-art AI. So, let's begin by exploring the foundational challenge: scaling reinforcement learning with LLMs. Reinforcement learning has become absolutely pivotal for pushing the boundaries of these models. We're talking about models from major players like OpenAI, DeepMind, DeepSeek AI, and Qwen, all of whom are leveraging RL to tackle those sophisticated, demanding problems like competitive programming, advanced math, or even multi-turn dialogue that requires deep, consistent reasoning.
That's right. Without RL, models tend to be very good at generating fluent, human-like text, sure, but they often lack the ability to consistently produce correct, high-quality, or logically sound outputs for truly complex, open-ended tasks.
Right, the competence part.
Exactly. RL provides that critical feedback loop. It allows the model to refine its internal policy to maximize some defined reward signal. For instance, in coding, the reward might be passing a suite of test cases. In math, it could be reaching the correct numerical answer after a multi-step derivation. It's how you get models to be not just fluent, but competent.
Okay. And to successfully scale that competence, especially with the, massive computational investment we're pouring into these gigantic models, what's the absolute first thing you need? Stability. It has to be foundational, right?
Absolutely.
You can't just keep pouring compute into a leaky bucket, can you? It's like trying to build a skyscraper on quicksand. No matter how much steel you add, if the foundation isn't stable, it's just going to sink or collapse.
Precisely. Maintaining stable and robust training dynamics is absolutely paramount. Without it, all that computational investment, those millions of GPU hours, the vast data sets, it's effectively wasted. Instability leads to divergence, where the model stops learning and its performance plummets. It can lead to oscillations, where it gets better, then worse, then better again, never really converging consistently. And ultimately, in the worst cases, it can lead to a complete breakdown in the learning process. You need a rock-solid, predictable foundation for continuous improvement, especially when dealing with models that have billions or even trillions of parameters. Any small numerical instability can just amplify catastrophically.
And this is where it gets really interesting and frankly a bit terrifying for researchers, I imagine. Despite its widespread use, current state-of-the-art RL algorithms, specifically Group Relative Policy Optimization or GRPO, they have severe stability issues when applied to training these gigantic language models at scale. The paper really highlights this as a major hurdle.
A huge hurdle. These issues often result in what's chillingly called catastrophic and irreversible model collapse. It's not just a temporary dip in performance. It means the model essentially breaks down so severely that you can't even recover it by reverting to a previous checkpoint.
Wow, irreversible.
Yeah, this is a critical barrier, a
Yeah.
brick wall that fundamentally hinders pushing the capability boundaries of LLMs through continued long-term RL training. Imagine putting in weeks, maybe months of GPU time, millions of dollars of compute, only for your cutting-edge model to suddenly irrevocably become useless. It's a researcher's absolute nightmare.
So what does this catastrophic and irreversible model collapse actually look like in practice? Is it like the model just starts generating complete nonsense, or does it become completely unresponsive? What are the symptoms?
It typically manifests as a rapid and severe degradation in performance across the board. Initially, the model might start generating outputs that are just slightly off, maybe subtly incorrect or less coherent.
Okay.
Then this can progress quickly to outputs that are repetitive, nonsensical, completely irrelevant to the query, or even just, well, gibberish. In the most severe cases, it might literally produce empty responses, or just a stream of random characters. But the key, as the paper emphasizes, is its irreversibility. Even if you try aggressive hyperparameter tuning, adjusting learning rates, batch sizes, clipping ranges, whatever, or even by reverting to a previous checkpoint from before the collapse and attempting to continue training, the model often just stays in this corrupted state.
So it's truly broken.
It's as if its internal representation, its very understanding of language and logic, has become fundamentally scrambled. It can't recover its coherent language modeling capabilities, even for simple tasks it previously mastered. It's far more severe than merely plateauing or slow convergence. It's a complete operational catastrophe.
That sounds like a nightmare scenario, a true bottleneck.
Hmm.
Okay, so to really understand why GSPO is such a breakthrough, we need to dissect GRPO's flaws. What's the fundamental root cause of this instability? Before we dig into why GRPO fails, let's quickly set the stage with definitions like the paper does. We're talking about an autoregressive language model, PIF, takes a query X, generates a response Y token by token. Then a verifier scores the pair, XY, gives it a single reward, RXY. Simple enough.
Right. And within this framework, the foundational algorithm is proximal policy optimization, PPO. PPO uses samples generated from an old policy, payload, and constrains the policy update within a proximal region of that old policy using a clipping mechanism.
Okay, the clipping keeps it from changing too fast.
Exactly. Prevents unstable updates. Specifically, PPO optimizes an objective using token-level importance ratios,
Huh?
WT, and an advantage term, ADIDIA, which is estimated by a separate value model.
Ah, the value model. The paper points out a core challenge with PPO is its heavy reliance on this value model. That sounds like significant technical overhead. Is it just the size, or are there deeper issues?
It's both, really. The value model is often as large as the policy model itself. So right there, you've doubled the memory and compute burden. Imagine a 30 billion parameter LLM. Now you need another 30 billion parameter value model. That's huge.
Yeah, prohibitive sometimes.
But beyond that, the algorithm's effectiveness hinges entirely on the reliability of this value estimate. And getting a reliable value model is inherently hard. It has to learn this complex function from states to values, often in a constantly shifting environment as the policy changes. Scaling that reliability to longer responses, more complex tasks, it's a massive challenge. The estimates can be noisy, inaccurate, leading to poor gradients for the policy.
It's like having a helper who's just as complex as you are, but whose main job is judging you, and if they're unreliable.
Exactly. Your main work suffers. And that's precisely where GRPO steps in, right? It tries to bypass that whole value model problem.
Right, tackling that specific PPO pain point.
Precisely. GRPO bypasses the value model by computing the relative advantage of each response within a group of responses to the same query. It optimizes an objective that still uses those token-level importance ratios, similar to PPO.
Yeah.
But the key difference is all tokens in a given response share the same advantage derived from the response's reward relative to its group. It simplifies the reward estimation, no separate value network.
Okay, so PPO has value model issues. GRPO tries to fix that, but still uses token-level calculations. Now, the paper identifies the core problem with GRPO. Its instability comes from a fundamental misapplication and invalidation of important sampling weights.
Mm.
What does that really mean? Why is it so fundamental it leads to collapse?
This is absolutely crucial. Think of important sampling like, okay, imagine trying to estimate the average opinion in a country by only talking to people from one very specific small town. Important sampling tries to correct for the fact that your small town sample, the old policy poll, might not represent the whole country, the new policy poll. It reweights the opinions. But for this correction to work, you need a representative sample, an average over many people, right, to smooth out the biases.
Okay, that makes sense. You need enough data points for the correction to be meaningful. So where does GRPO go wrong?
GRPO applies the importance weight, that correction factor, at each individual token position. Instead of averaging over multiple sequences, it's like trying to judge the whole country's opinion based on one person's opinion at a time, reweighted individually. For each token, Kate, the weight with APTIA is based on a single sample from that specific next token distribution under the old policy. This single sample, token-level application, just fails to perform its intended distribution correction role. It doesn't average out the noise.
So instead of correcting, it's adding noise, like trying to hear a melody when every instrument's volume is fluctuating wildly and independently.
Exactly. Instead of correcting for the distributional mismatch, it introduces a significant amount of high-variance noise into the training gradients. And this noise accumulates catastrophically over long sequences because you're applying this noisy correction at every single token, maybe hundreds or thousands of times. And what's worse, this noise gets exacerbated by the clipping mechanism, the very thing meant to stabilize things. Instead of smoothly limiting updates, the clipping interacts with this high variance noise unpredictably, sometimes pushing the policy in completely wrong directions. That leads straight to collapse.
And that combination, the noisy token weights, the accumulating error, the problematic clipping interaction leads directly to that irreversible model collapse. No coming back.
Precisely. The empirical observation detailed in the paper is stark. Once collapse occurs, resuming training is useless. You can't recover the model. Hyperparameter tuning, reverting checkpoints, nothing works. The fundamental signal-to-noise ratio in the gradients is just destroyed. The model can't learn effectively anymore. It's lost its way in a sea of noise.
This suggests a deep flaw in GRPO's design, more than just a bug. The paper states the unit of optimization objective should match the unit of reward. Can you elaborate on this technical point? Why is that alignment so critical?
This is a core principle GRPO violates. The reward, RXY, is given for the entire sequence Y, a single score for the whole output.
Right, the whole answer, not each word.
Exactly. But GRPO attempts to apply off-policy correction and optimize at the token level using WIT. This mismatch means the individual token-level weights are fundamentally problematic for an overall sequence reward. The feedback signal is global, holistic, but the learning signal is granular and misaligned. It causes inconsistencies and, critically, that high variance in the gradients. It's like trying to conduct an orchestra by giving feedback to individual players on single notes, ignoring the harmony of the whole piece. You'll just get noise.
That's a powerful analogy. So if this unit mismatch is such a key problem in LLM-RL, does this insight apply more broadly? Are there other areas in ML where this might be a hidden issue? What aren't the papers talking about here?
That's a really important question, and I think yes, absolutely. This principle likely extends far beyond LLMs. Any system where a global, coarse-grained reward is given only after a sequence of actions, but optimization tries to correct at a finer-grained level. It could face similar issues. Think about robotics, for example. A robot gets a reward after assembling a whole product, maybe many steps. If you try to apply important sampling correction at the level of individual motor commands within that sequence without considering the overall task success, you could get instability, jerky movements,
Yeah, I can see that.
or maybe complex control systems like optimizing a chemical plant or managing a power grid. Rewards are often delayed, reflecting the overall system state, not single valve adjustments. Applying corrections too granularly could destabilize the whole system. This info from the Qwen team, while focused on LLMs, really highlights a potentially universal principle for stable and efficient RL. Align the learning signal with the feedback signal.
Okay, this perfectly sets the stage for GSPO, Group Sequence Policy Optimization. It directly tackles this misalignment. The paper says its key innovation is defining the importance ratio based on sequence likelihood. What was the simple observation that led to this?
Well, while those token-level weights were clearly problematic in GRPO, the Qwen team observed something elegant: the sequence-level importance weight. That is, the ratio of the current policy's probability of generating the entire response Y to the old policy's probability px puque x. This ratio does have a clear, robust, mathematically sound meaning for language generation.
Oh, okay.
It directly reflects how much an entire sampled response y deviates from the current policy PUC compared to the old one PUC. This naturally and perfectly aligns with the sequence-level reward the verifier provides. Reward for the sequence, correct based on the sequence likelihood. It restores that fundamental alignment.
So GSPO just ditches the token-level objective entirely, moves to sequence-level optimization. What does that look like in the objective function? How does it work mathematically, broadly speaking?
Broadly, the GSPO objective sums over responses U in a group. For each response, it takes the minimum of two terms. First, the sequence importance ratio, free times the group-based advantage A. Second, a clipped version of that term to keep updates safe, like PPO.
Okay, still got clip it.
Still got clipping, yes. The advantage I is still calculated relative to the group. Reward minus mean reward, normalized by standard deviation, helps stabilize the reward signal itself. But the crucial difference is that importance ratio, CQ. Conceptually, it's the ratio of the current policy's sequence likelihood to the old policy's sequence likelihood. But importantly, it includes that youth root, essentially averaging the log likelihood ratios over the sequence lengths. That root is key for stability.
Right. I noticed that 1e term in the exponent of Seeth, this length normalization. Seems subtle, but you're saying it's critical. Why?
Oh, it's incredibly clever and profoundly important for stability. Its purpose is basically twofold. Reduce variance and keep psi in a consistent numerical range no matter how long the sequence Y is.
Oh.
Without it, imagine a really long sequence, like 1,000 tokens.
Sure.
If just a few tokens at the end have a wildly different likelihood under the new policy, that could make the entire sequence importance ratio explode or vanish, leading to totally unstable gradients. Also, sequences of different lengths would naturally have importance ratios spanning huge ranges, making tuning clipping ranges almost impossible.
Right, standardizing the signal strength.
Exactly. It standardizes the strength of the signal across different lengths. It ensures the clipping mechanism works consistently for short answers or long essays. It prevents a super long but slightly off response from having this huge, noisy impact. The impact becomes proportional to its overall deviation, averaged out.
And crucially, GSPO applies clipping to entire responses, not individual tokens, right? Matching that sequence level reward again.
Perfectly. It reinforces that fundamental principle. If the whole sequence's likelihood ratio deviates too much, the whole sequence gets clipped or discarded from the update. No more token level fiddling.
And the paper notes the clipping ranges differ by orders of magnitude between GSPO and GRPO. That's a huge flag, isn't it? Suggests they're fundamentally different beasts numerically.
It absolutely is. A very telling empirical observation. GRPO's ranges are maybe 0.2 to 0.27, so plus minus 20, 27% fluctuation allowed at the token level. GSPO's ranges, orders of magnitude smaller, like 3E4 to 4E4, tiny.
Wow.
This stark difference just screams that GSPO's sequence-level ratios, especially with length normalization, are inherently far more stable. They live in a much tighter, controlled numerical space, allowing for much narrower, more effective clipping bounds. It signals GSPO is handling the numbers in a vastly more robust way.
Okay, let's get slightly deeper into the math, into the gradient analysis. This is where the learning actually happens. What's the fundamental difference in how GSPO and GRPO weight the gradients of the log likelihoods of tokens?
Okay, so in GRPO's gradient, each token in a sequence Y gets weighted by its own individual token level importance weight, by T. As we said, these weights are unequal, they can vary wildly, they're noisy. They accumulate unpredictably across the sequence. These high variance weights corrupt the gradient signal. It's like trying to steer using dozens of noisy compasses.
So each token's push on the gradient is unevenly amplified or suppressed by its own noisy weight, destabilizing the whole update. How does GSPO differ?
Correct. That variability corrupts the GRPO gradient. In stark contrast, GSPO weights all tokens in a response equally when calculating the gradient. It applies that single, stable, sequence-level importance ratio uniformly across all tokens in that sequence E. This fundamentally eliminates that source of high variance instability from GRPO. It's a much cleaner, more consistent signal applied everywhere in the sequence. Equal weighting is key.
Like one good, stable compass for the whole journey? Okay. But then the paper introduces a variant, GSPO token. This seems counterintuitive. Why bring back a token-level objective if sequence-level GSPO is so much better? Isn't that a step backward?
It's more about adding flexibility for specific, advanced RL scenarios, not really a step back. Think about complex multi-turn dialogues. The context changes turn by turn. You might need to adjust advantages at a finer level than the entire long dialogue.
Okay, for more granular rewards sometime.
Exactly. GSPO token provides that flexibility. It allows for token-wise advantage customization, but crucially, without reintroducing GRPO's instability. The way it does this is quite neat.
How does it manage that? How does GSPO token give token level advantage flexibility but keep GSPO stability? What's the trick?
It cleverly uses the sequence level importance ratio psi from the original GSPO, but it applies a stop gradient operations SGI. This means psi's value is used, but its gradients don't flow back through it during backpropagation. Then it effectively sets the token level importance weight SIC to be numerically equal to this stopped psi for every token T. So if all the token advantages IRO are the same as the sequence advantage IRO, the objective and gradient are identical to standard GSPO.
Okay.
But it provides the mechanism to set different arrow values per token if needed for those complex scenarios. By stopping the gradient on psi, it avoids propagating the high variance calculations associated with individual token ratios that plague GRPO. So stability is maintained, but you gain granular control over advantages when necessary. It's elegant.
The theory sounds solid, really addressing GRPO's core flaws. But what about the experiments? Did it work in practice? What model did they use and what benchmarks did they test it on?
They used a serious testbed. A cold start Qwen 3 30B A3B base model. That's a 30 billion parameter MoE model, not a toy example.
Right, state-of-the-art stuff.
Exactly. Performance was measured on tough benchmarks. AM24 for competition math, pass at 1 over 32 samples. Live code bench for general coding, pass at 1 over 8 samples. And code forces for competitive programming, using the ELO rating. Their training setup involved partitioning rollout batches into 4 mini-batches for updates, pretty standard for large-scale RL. And they carefully tuned clipping ranges, tight 3E4 to 4E4 for GSPO, and the optimal 0.2 to 0.27 for GRPO for a fair fight.
And the results, figure 1 in the paper looked pretty striking. What did it show about stability and efficiency?
Figure 1 is very clear. GSPO training proceeds remarkably stably right through the whole process. You see continuous robust performance improvement as compute increases, as queries get updated, as generation length extends. This is in sharp contrast to the instability and collapses often seen with GRPO at scale. And moreover, GSPO showed superior training efficiency over GRPO. Given the same compute budget, the same number of queries consumed.
Same resources.
Same resources. GSPO delivered notably better training accuracy and benchmark performance across all metrics. Math, coding, competitive programming.
So it's not just not collapsing, which is huge, but it's actively performing better, more efficiently, with the same resources. It's getting more bang for the buck.
Exactly right. It indicates a much more effective use of the training data and compute. The stability lets you invest more compute confidently, expending predictable gains without fearing collapse. And the efficiency means those gains come faster at a lower effective cost. The paper explicitly credits GSPO for the success of their latest Qwen 3 models, proving its real-world efficacy in unlocking RL scaling. It's a fundamental enabler.
Now, here's that really fascinating counterintuitive bit from Figure 2. GSPO actually clips way more tokens than GRPO, 2 orders of magnitude more, yet it's more efficient. That feels wrong instinctively, doesn't it? Less guidance should mean more data used, better efficiency. Why isn't that the case here?
It is very curious, but it's a key finding that really shines a light on GRPO's issues versus GSPO's strength. GRPO's clipping fractions are tiny, like 0.0013, meaning only about 0.13% of tokens get clipped. GSPO, its clipping fractions are way higher, up to 0.15, meaning 15% of its sequences get clipped or affected by clipping. So even though GSPO is effectively throwing out way more potential gradient information by clipping whole sequences, it still achieves higher efficiency and better performance.
So what does that tell us about GRPO's gradients? If GSPO uses less total data effectively but does better, it implies GRPO's data or how it used it wasn't very good quality.
That's a perfect way to put it. It strongly suggests GRPO's token-level gradient estimates are inherently noisy, highly variable, and just inefficient for exploiting the samples. Clipping is meant to stop bad samples from corrupting learning. But GRPO's gradients seem so inherently noisy that even with minimal clipping, they lead to worse outcomes and collapse. GSPO's sequence-level approach gives a cleaner signal. Even though it clips more overall, the remaining signal is higher quality and more coherent. So it learns better from less, but cleaner data. It's about signal quality, not just quantity. A really profound insight.
Okay, let's shift gears to the MoE revolution. Mixture of experts models are hot right now, super efficient, scalable, the future, maybe. But the paper points out unique stability challenges for RL training with MoEs compared to dense models. What's the specific technical issue there?
The main technical challenge with MoEs and RL is something the paper calls expert activation volatility. Because MOEs are sparse, only some experts activate for any given input, unlike dense models where everything fires. After a gradient update changes the policy slightly, the specific set of experts activated for the exact same input or response can change significantly. The routing logic shifts.
Okay, the network path changes internally, and they gave an example, right? How much volatility are we talking about?
Yeah, it's quite significant. With their 48-layer Qwen 330B A3B base MOE model, they found roughly 10% of the activated experts were different under the new policy compared to the old policy for the same sample after just one RL gradient update.
10% change every update. Wow.
Yeah, it's not rare, it's constant. And it gets even more pronounced in deeper MOE models with more complex routing layers.
And this expert activation volatility messes directly with GRPO's token level importance ratios, making its instability even worse.
Absolutely. When the activated experts change for a token, the POFOLD YT values are literally computed by different bits of the network. This makes the ratio fluctuate wildly and, frankly, invalidates it because the underlying functions generating those likelihoods are different between POF and VOLD. GRPO relies on that ratio being somewhat consistent. MOEs inherently break that consistency at the token level. It's a direct conflict.
So GRPO needed a serious workaround for MOEs, a band-aid to even make it work.
They did. They used a strategy called routing replay. Basically, they'd cache which experts were activated by the old policy pool during data collection. Then, when computing the importance ratios for the new policy pool, they'd force pool to use the exact same cached routing paths, the same experts that POFOLD had used.
Okay, forcing consistency. But that sounds like a hack. Extra memory, extra communication.
Right.
And doesn't it limit the MOE model itself? Like putting a leash on it?
It was definitely a technical compromise, a big engineering lift. Routing replay was essential for GRPO MOE training to converge at all. Figure 3 shows GRPO fails without it. But yeah, it cost a lot. Extra memory for caching, extra communication, overhead, and distributed training. And you're right, crucially, it could limit the MOE's potential by forcing it to reuse old, maybe suboptimal routing paths. It prevents the MOE from fully leveraging its dynamic routing advantage under the updated policy. It worked to stop collapse, but maybe capped performance and added complexity.
So if routing replay was this complex limiting fix, how does GSPO handle MOEs? How does it simplify things and solve this volatility issue?
GSPO just eliminates the need for routing replay entirely. Figure 1 shows it clearly. GSPO computes its sequence-level ratios side-normally, converges stably, optimizes fine with no special MOE hacks.
It just works. That's huge for MOEs.
It's a massive simplification and a testament to its robust design.
But why is GSPO immune? The experts are still changing underneath at the token level, right? What's the insight?
The key insight goes back to GSPO, focusing only on the overall sequence likelihood, pi(x). It's not sensitive to the individual token likelihoods or which specific experts fired for each token. While the exact computation path might change token by token due to volatility, the MOE model as a whole still maintains its underlying language modeling capability. So the overall probability of generating the sequence tends to remain relatively stable. It doesn't fluctuate wildly just because a few experts swapped out internally. GSPO's sequence-level view smooths out those micro-level fluctuations. It sees the forest, which remains stable, not just the volatile trees.
So GSPO not only simplifies and stabilizes MOE training, but it lets the MOE model actually use its dynamic routing fully, takes the leash off.
Precisely, it's a fundamental resolution. By ditching routing replay, GSPO allows MOEs to fully leverage their dynamic expert selection, potentially unlocking performance and efficiency gains that were previously suppressed. Simpler engineering, less overhead, and crucially, letting the MOE model achieve its full potential without artificial constraints.
Okay, beyond stability and MOE performance, the paper hints at another really practical benefit for the whole RL infrastructure. These precision discrepancies between training and inference engines.
Yeah.
Why is that a problem now?
Yes, this is a subtle but very real pain point in large-scale AI pipelines.
Yeah.
Training engines like Megatron and inference engines like VLLM or SGLang,
Right.
they're optimized differently. They often have tiny differences in numerical precision, maybe how they handle floating point math or mixed precision.
Okay.
Now, in RL, you usually generate responses using the fast inference engine. But then for accuracy in the RL update, especially for those GRPO token ratios, you typically have to recompute the likelihoods of those responses under the old policy using the trading engine to ensure perfect numerical consistency.
Oof, recomputing. That sounds expensive.
It is. It adds significant overhead compute time, data transfer, just running parts of the forward pass again on a different system to get consistent numbers. It's an efficiency tax.
And GSPO might avoid this. How does sequence-level likelihood make it more tolerant to these small precision differences?
Because GSPO only cares about the sequence-level likelihood ratio. The cumulative effect of tiny precision errors at the individual token level tends to average out, get smoothed away, when you aggregate likelihoods across the entire sequence. Micro-level numerical differences become pretty insignificant at the macro sequence level. So GSPO sequence ratio psi is inherently much more robust to these minor variations between engines.
So you might be able to just use the likelihoods from the fast inference engine directly in the GSPO update, cut out the whole recomputation step.
Exactly. That's the potential benefit. Avoiding that entire recomputation step would be a massive win for efficiency and pipeline simplicity. Hugely beneficial for things like partial rollouts, multi-turn RL, and especially these newer disaggregated training inference setups where compute is physically separate. Trusting the inference engine's likelihoods directly streamlines data flow, reduces latency, saves resources.
If that holds up, what does it mean for the future speed of RL pipelines? Faster iteration cycles, quicker AI progress.
It's a really important operational point. Streamlining data flow, cutting redundant computation. It absolutely could accelerate the entire RL development loop. Less time on data wrangling and recomputation means more time for actual model iteration, experimenting with new ideas, faster fine-tuning. It could really compress the time from research to deployment, getting better models out faster. It's an infrastructural speed up, not just algorithmic.
Okay, let's wrap up this deep dive. GSPO, new RL algorithm for LLMs. What's its core innovation in a nutshell?
It redefines importance ratios based on sequence likelihood. It performs sequence-level clipping, rewarding, and optimization. This corrects the fundamental principle of importance sampling that GRPO misapplied, aligning optimization with the sequence-level reward. Much more stable.
And the big three practical takeaways. What does GSPO achieve?
Okay, three things. First, remarkably superior training stability, efficiency, and performance compared to GRPO. No more catastrophic collapse, just robust improvement. Second, its particular effectiveness for large-scale MoE training, fundamentally solving expert activation volatility without complex workarounds like routing replay. And third, the potential to simplify RL infrastructure by being more tolerant of precision discrepancies, possibly eliminating costly recomputation steps.
And the Qwen team directly credits GSPO for the big improvements in their latest Qwen 3 models. That's a powerful real-world validation.
Absolutely. It positions GSPO as a scalable algorithmic cornerstone for the next generation of LLMs. We really see it laying the foundation for continued aggressive advances in large-scale RL, pushing models to fundamentally new levels of intelligence and capability. It's a foundational shift.
So as you, our listeners, think about the future of AI, consider this. If one algorithmic innovation like GSPO can unlock such huge gains in stability and efficiency for the biggest models, what other subtle shifts and fundamental principles might be out there waiting to unleash the next big leap in AI? It's not always about just more compute. Sometimes it's about finding a smarter way to learn. Thank you for joining us on this deep dive into GSPO. We'll be back soon with more insights into the bleeding edge of AI.